From now on, you should be able to see the streaming on my YouTube channel. Okay, so that if you miss the lecture, you can always go to my YouTube channel and see and listen to the recorded lecture again. Please try all these tools and tell me if everything is working or not. If there are some problems, you tell me so that I can intervene and set up things in order to provide you with all these technical tools. Okay, now I pose you a question. Can you understand my way of speaking? It is too complicated, my English. I am speaking not clearly. Nobody answers. This means that I'm speaking clearly. Let's see, somebody wants to come in. Sometimes I would like to have some feedbacks from you boys, because it is very, very difficult and sad for me to speak with the screen, while I like to speak with people. This is why from time to time I will ask you some feedback in order to be sure that there is somebody that is listening, really listening to me, and that I'm not only a lonely stupid speaking with a screen. You understand my point? I hope so. So let's go back to the class and let's switch to an interesting aspect, that is that of the definition of environment. This is ecological modeling, modeling and control of environmental systems. What are environmental systems? Sorry, I'm meeting a lot of people that are connecting late. Environmental systems are based on the definition of environment. There are several definitions of environment, depending on the context in which these definitions are used or are provided for. One of the most useful, at least according to my understanding, is that provided by the European Community Council in 1973. That says that the environment is the set of elements that, in the complexity of their relations, constitute the framework, the habitat, and the condition of human life, which are in reality or what are perceived. So let's spend a little time on this definition. The set of elements. So we recognize that environment is made up of a set of different elements. We recognize that environment is a complex object. In particular, environmental systems are complex objects that are made up of a set of elements that are interrelated each other, and the complexity of their relationships constitutes what we may call the framework of the habitat, the conditions for human life. So we see that this definition is very anthropogenic, in the sense that we give a definition from an anthropic perspective. So environment, from the ecological scientists, from the ecologists, is a set of elements that are interrelated in a complex way in order to constitute a framework that we may also call the habitat or conditions that may foster human life. An important aspect of this definition resides in the last part of a sentence, which are in reality or what are perceived. This means that given this very anthropogenic definition, we immediately recognize, and we set it clearly in the definition, that the conditions, the habitats, are perceived by us. This means that the perception of environmental systems may change according to the different scientists that change or give their own personal interpretation or perception of environment. So you see that we are trying to make operative, practical, the definition of something, but it is in principle very difficult to define as a general term, because being a human perspective, different humans may have different perceptions of environmental conditions. So this is something that the environmental engineer has always to keep in mind. What the environmental engineer is dealing with is not the reality in absolute terms. Instead, it is a kind of subjective perception of real structures or real ecological or environmental systems. At this point, it is important to make a distinction between environmental engineering and ecological engineering. You are environmental engineers, so you will deal with environmental engineering. Environmental engineering deals with purpose-driven design structures. This means that the structures that the environmental engineers are able to build, to perceive, to conceive are typically purpose-driven. Means, for example, the environmental engineer often deals with the problem of wastewater purification. This is a typical example of a purpose-driven design effort in which the environmental engineer designs and builds a wastewater treatment plant with a specific purpose or with a specific object. So the design from the environmental engineering point of view is driven by the purpose, the application, for example, water purification. This is slightly different from ecological engineering, but is somewhere in between engineering and biology. So it is more related to the ecology or ecological aspect of biology. What is ecology? Ecology is a branch of biology in which a biologist tends to describe exactly what we have said before: complex system with several elements in complex interactions. In order to employ this kind of description, ecology, that is, if you want, a system theory branch or a biology branch into system theory, in which we provide mathematical models in order to describe biological interactions. This is ecological engineering. Differently from environmental engineering, ecological engineering is more a process-oriented design structures. So the structures that designs the ecological engineer are more process-oriented, more than purpose-driven. This has to do with the fact that engineering is a practical science in which engineers are requested to build construction structures, intervene into systems, modify the behavior of systems. This is all purpose-driven. While in the case of ecological engineering, we are more interested to the process. So we are putting our focus more on the process of transformation, if you want, exchanges or flow of resources, consumption of resources, conservation, sustainability, and so on. These are all concepts that are more dealt with by ecological engineers. Ecological modeling techniques are specific of ecological engineering and are used to predict ecosystem structure and function in ecosystem creation and restoration. So you see that from the ecological point of view, from ecological engineer will employ ecological models or ecological modeling techniques in order to have prediction of ecosystem structures and behavior. So these are important tools in order to intervene in the creation and restoration of ecosystems. Ecological engineering has to be flexible, iterative process of design in which the designer must continually update goals, essence, typologies, and processes of realization. This is the definition given by Mcesy in 2005, in which Mcesy tries to explain which is the role of ecological modeling into environmental engineering, and we may call this role ecological engineering, that is a process-oriented approach in designing structure. In order to use a process-oriented approach, the typical tool or the typical instrument is that of mathematical modeling. Okay, do you have any questions? From a graphical perspective point of view, we may say that in ecological engineering, we deal with analysis and control for integrated management. So while environmental engineering has to do more with the construction of purpose-driven structures, ecological engineering has to do more with the design of process-oriented descriptions or models. This is important in order to gather analysis and control, and in order to build up integrated management systems. For example, we may see environmental monitoring in general. This is observation of ecosystems. This is a starting point. Then we may switch to water quality monitoring. So we may focus the general analysis of environment on specific aspects, in particular of utmost relevance for environmental engineers, water quality, for example. In your professional life, you will often ask to give appraisals of water quality. So this is water quality monitoring. Then, from a practical point of view, the ecological engineer will deal with designing and implementation of various ecological technologies or eco-technologies. For example, wetland system for water purification is an eco-technology. Eco-technology, yes. Or an ecological technology. Or, for example, forest restoration or diversity control. These are all eco-technological approaches. But two of the very important tools for the ecological engineering are laboratory analysis and modeling. Laboratory analysis means chemical analysis of environmental samples, maybe these maybe water samples or soil, land samples, or organism samples. These are all laboratory analysis techniques that provide us data for the analysis or observation of a system. But the step forward that is given by the ecological engineer is that of building a description or a paradigm or a model of a system I am observing. So building a model means synthesizing the analytical data coming from analysis, laboratory analysis, into a synthetic outcomes that is given by the model. So the model ends up with a description of the system that provides us with ability or the possibility of analyzing scenarios or future behaviors of natural systems or environmental systems. Am I too complicated, or you can follow me? I know it sounds like I'm very abstract here, but you will see that little by little we will step into the more engineer-friendly environment of practical applications. So we are starting with some philosophy or epistemology, or some philosophical basis of knowledge management, and little by little we will try to transform these philosophical concepts into more practical concepts. By the end of the class, I hope you will be able to practically construct a mathematical model of a real system. Okay, you probably will not be able to cool, but at least you will have the tools, the basic information that will guide you in finding the resources that you need, especially in understanding what you will read, finding and understanding the resources that you will need in order to build a mathematical model. So what we will discuss in this class, we'll start with an introduction. So we are here now. Today, this is the introduction. Then we will go more in detail into the stages of a modeling procedure. So this will take some lectures in which we will go step by step into the procedure of building ecological models or environmental systems models. I anticipate that there will be 8 fundamental steps that may be subject of the final exam. During these procedures, or if you want, one of the first more important steps of the modeling procedure is that of the model conceptualizations. We'll give some example of what we mean by model conceptualization. Essentially, this means that we are starting to think at the system, real system, and we are starting to sort out the various elements or the various tools of a description or the various concepts that we will need to describe the system we want to describe. With model conceptualization, we deal also with the problem of defining the complexity of a model. We started our lecture by saying that environmental systems are complex systems, ecological systems are complex systems. So complexity is one of the characteristics of living systems. We will discuss a lot, or we'll cite very often complexity and complex systems. And one of the problems the ecological model or the environmental engineer will be faced when he started to build an ecological model is that of defining the appropriate level of complexity, the appropriate complexity of your description. What is the appropriate complexity of your description? Your description will be adequately complex if the complexity of your description is consistent with the complexity of a system you want to describe. Please note, you want to describe. This means that the complexity of the system you want to describe depends exactly on the focus of your application. This means the environmental engineer has a particular top problem, an issue to deal with. Then he has to make a first analysis of the complexity of this issue in order to conceptualize a model that is able to describe the complexity, conceptualize an adequately complex model that is able to copy and to cover the complexity of the systems I want to study. So you understand that the characteristics in terms of complexity of a model depends on the object or on the system you want to model. I know, I understand, but this sounds to you very exotic, quite far from engineering. Don't worry, because little by little you will understand that instead this is really a way of dealing with complex systems, so understanding and defining the right level of complexity of our description. Once we have introduced the stage of modeling procedure and the conceptualization of model, then we will go into more details about physical, chemical, and biological processes. This is the core of the class. Point 4 is the core of a class in which I will give you an overview of physical, chemical, and biological processes from the ecological engineer point of view. And then we will try to translate these ecological aspects into more environmental modeling aspects. So I will try to give you a description or an overview of how we can mathematically describe these physical, chemical, and biological processes. So I will give you an overview of what are, according to us, relevant processes in the physical, chemical, and biological realms. And then I will give you a set of tools that may help the environmental engineer to build up a mathematical model of the environmental system. During these discussions, we will deal with some very specific issues. For example, that of limiting factors. As we will see, limitation or limiting factor is a very relevant aspect in order to describe living systems. Unlimited, non-limitation does not exist in biology. Living systems, by their definition, are always somehow limited, and we will give some examples of this limitation. We may have space, resource, time limitation, conceptual limitation, and so on. All the understanding of the behavior, the understanding of the role of these limiting factors, as we will see, is of utmost importance in order to build a consistent description of an environmental system or of a living system. I will often confuse living system, environmental system, living object, and so on, because what we are talking in this class is objects that we are talking about objects that display the very peculiar characteristics of being living object. Is a very deep distinction. I mean, it is a basic distinction. In our observation of nature, we may distinguish between living and non-living objects. I think that all of you will agree with me that there are living and non-living objects, and but these two different classes of objects are different. In this class, we are mainly dealing with living objects. So environmental system, ecosystem, living objects, organisms, plants, animals, these are all different manifestations of life. And we will have an entire classroom discussing what is life. Very good question. What is life? I hope that in a week or two, you will be able to provide your own answer to this question. Then, in the procedure of building a model of environmental system, we will often employ very specific tools, like, for example, metabolic models. You may have already heard of the term metabolic. What is metabolism? Metabolism is the flow of energy per unit time, per unit mass or unit volume of a given system. So it is metabolism is a flow of energy, or better, a density, a flow density, an energy flow density. These metabolic models. So when we talk about metabolic modeling, this means that we are describing essentially the exchanges of energies between the different systems or between the different elements that build up our complex ecological system. Our tool will be that of ecotoxicology. Maybe I will give you an outline of ecotoxicology, but I believe that you have already an ecotoxicological class in your curricula. So I give, for already known several concepts concerning ecotoxicology. If this is not the case, please stop me and ask me to go into more details about ecotoxicology. And then, if we are good enough, we will also give a look to trophic networks. It is, if you want, one of the most advanced way of describing energy flows and exchanges into living system. The way is that this way we describe by building networks of arcs and nodes, and these networks are assumed to be somehow descriptive of interactions between the different elements of the system. So you see, we have started by saying that environmental systems are complex systems made up of several elements, for example, different animals or different plants or different processes or different climatic conditions or atmospheric or whatever. These elements are all connected into a complex interrelationships that end up with a complex ecological system. And now we would be happy to be able to construct a mathematical description or a mathematical model of this complex system. Okay. Okay, we will have a complete lecture in which we will try to describe the topic of distributed parameters models. As we will see soon, we may classify ecological models or mathematical models in reality into two very broad classes: aggregated and distributed parameters. Aggregated parameters models are models in which we do not consider spatial or temporal heterogeneities. Instead, we consider our system as a punctual, zero-dimensional, instantaneous system. This is the situation in which you have aggregated parameters approaches. In reality, when we describe environmental systems, we may describe systems that interact with the environment, so systems that are somehow geographically distributed. So you understand that the approach of aggregated parameters, especially when you deal with environmental systems or real ecological systems, is not appropriate. So we will need to do some kind of geographical descriptions in terms of, for example, GIS. I think many of you know what GIS are. The acronym GIS stands for Geographical Information Systems. Geographical Information Systems are software tools that allows us to distribute our knowledge of reality onto geographical coordinated systems. This means that if you want to describe some kind of real region, geographical region in space, you will need to resort to this kind of tools, GIS. GIS are softwares that describe the characteristics, the different characteristics of the different aspects of the environment by spreading this description onto this, a geographic map or geographic description of a system. Okay, so we will have a lecture that is distributed parameters modeling, in which I will show you how the very complex application of ecological modeling may be pushed up to employ geographical description through GIS, for example, in which you may construct description that are geographically projected or geographically located of ecosystems. And in order to explain this approach, I will present you a software tool, a model that is called MONERIS, an acronym that stands for Modeling Nutrient Emissions into River System. you may imagine as environmental engineer, you may be aware, but nutrient loads are very important or relevant aspects. So being able to predict nutrient loads generated by environmental systems is a very important, powerful tool in order to understand the effect or the linkages, the interrelationships between environmental systems and the surrounding environment in which the environmental system it is embedded in. Normally, I give also some lecture on wastewater treatment plants. I don't know if we will have time this year, but instead I will give you an entire lecture on ecosystem services and the use of these concepts into models for environmental impact assessment. So, environmental impact assessment, I am sure you know, it is one of the issues or one of the topics of relevance for an environmental engineer. So typically when we do environmental impact assessment, the environmental engineer is requested to build a description, a model of a given system in order to evaluate its environmental impact. And a cornerstone concept in doing this kind of analysis is the concept of ecosystem services. What are ecosystem services? Are services that are provided to us, humans, but also to nature in general, by natural systems, by ecosystems. We will see that we may give a description of the relevance of different ecosystems in terms of the practical services that these systems provide. Do you have any questions? Okay, give me 1 minute. I need to drink some water and to rest the voice a little bit. Okay, shall I continue? I hope that everybody here in the class is able to connect.
Yes, sir, you can continue.
To connect to the Moodle course web page. I assume you are able to do that, or I assume that you already did that because you have been registered into the web page, the Moodle web page, so that I gathered your email, and the email I sent you a couple of days ago were sent exactly to those email registered or recorded onto class Moodle web page. All the resources of the course will be found on this web page on Moodle. Among the various resources that you will find, there are the lectures that I'm presenting, like the one that I'm presenting today. It is called Introduction, and it is the first lecture, so you can download a PDF of this lecture from the Moodle web page. You can download, for example, also a calendar of the lectures that we will be holding next 3 weeks. This is the calendar, the one that I'm displaying now. So, as you can see, in general, we will have 4 classes per week: Monday, Tuesday, Wednesday, and Thursday, typically at 10 a.m. Yaoundé time. Each class will last 2 hours, or maybe something more. Ideally 1.5 to 2.5 hours. So this is the timing between which I normally am able to give my lectures. The first week will start today, for example, introduction. I will give you very soon some generalities about models, physical and mathematical models, distinction between research and management models, holism and reductionisms, and ecosystems as an object of research. This is the topic of today's lectures. Tomorrow we will give an history of evolution lecture in which we will introduce some general concepts like epigenetics, modeling elements, model types, and so on. We'll introduce conceptual diagrams and model conceptualization on Wednesday. And on Thursday, we will deal with the last steps on the last step needed in the procedure of building ecological model. Then we switch to next week, in which we will introduce the processes. So the first day, Monday of next week, we will deal with physical processes. So this has to do with ecotoxicology, absorption, transport, and chemical reactions. We'll deal with settling and suspension on Tuesday. We'll introduce energetical factors. And then we'll give an introduction to distributed parameters modeling is what I was talking about before. I will introduce the model for describing nutrient emissions into river systems. These are GIS, distributed parameter models, is the most complex part, if you want, of a modeling approach we will touch during this class. On Thursday next week, we will discuss about ecosystem services, the concept, this very powerful concept that gives a new perspective on our way of understanding the behavior of ecosystems, in particular of understanding the quality of ecosystems. And then we will go the third week, 24th of May, into more specific models like metabolic models or models specific for describing processes as light extinction or processes like photosynthesis, primary production, algal growth. We'll introduce models to deal with light and nutrient limitations, and we will start an introduction onto trophic network modeling or network analysis. In my idea, you should be ready to give your examination on Monday, May the 31st. Of course, this data may be discussed and will be the responsibility of Aisha, the delegate, to collect your willings and to decide in class which will be the most suitable date for sustaining the exam. Do you have any questions about this very relevant topic? No questions. Very good. Please wait for me 1 minute. I'll be back soon. Okay, let's go back. I would like to have some feedback from you. Do you have any questions? No questions. Okay, let's see if I can, how do you say, I can wake your interest. Let's start with some generalities concerning mathematical models. These are very general concepts applying to all mathematical models, and in particular applying also to models used to describe environmental real systems. The first issue, mathematical modeler deals with is that of the scales. When you start building a mathematical model, or when you start conceptualizing mathematical model, it is a good starting point, but of discussing the scales in terms of temporal, seconds, minutes, weeks, months, years, centuries, or special scales, millimeters, centimeters, kilometers, meters, kilometers, and so on. Of course, you may understand that the various processes that may or may not be relevant to a particular ecological system may have, for example, a resolution, very high temporal resolution, for example, that of physical processes. If you study the movement of an object, you may, for example, if you are dealing with a dynamical study of something, you may, for example, describe the process with a resolution of seconds. While, for example, if you deal with ecological or biological processes, like, for example, plant growth, then seconds, it is not probably the right temporal scale. Instead, you may find more useful use scale, a temporal scale of days, sometimes months, more often seasons. So you see that the temporal scale depends on the object you're studying and on the type of description you want to give. So it is the modeler that, in terms of the object it wants to describe, defines, first of all, the temporal scales he will apply. Analogously for spatial scales, for example, if the process you want to describe is a kind of chemical process, then your spatial scale will be that of centimeter. While if, for example, you want to describe a process but it is a landscape process, like, for example, the growth of a forest, or the growth or the problem of land erosion, soil erosion, and so on, the spatial scale will be that of some meters, hundreds of meters, maybe kilometers, sometimes thousands of kilometers, depending on the type of system you want to describe. For example, if you want to describe a nutrient generation to a river system, you will select a temporal scale, but it is at least seasonal, or annual, because as your understanding of ecological engineering, of environmental engineering, you know that the process that govern nutrient generation are relevant on scales of seasons, because according to the different season, so different climatic conditions, you will have different process of nutrient generation. In terms of spatial scales, if you want to model nutrient generation for example, on a river basin or on a river catchment, then the scale will be that of a catchment. So we are discussing about square meters, square kilometers, hectares, and so on. The other very important point that the ecological modeler has to keep in mind always, that the model is not the reality. Of course, you will say, oh, very good, what interesting. You have to keep this in mind, because very often, after you're working for several months on a model, you really believe in your newborn creature, the mathematical model of a system you want to describe, and it may happen that you forget that the model that you have built is not the reality itself. It's just a sketch or a description of some aspects of a reality that the modeler finds relevant in order to deal with the issue and the problem he has to deal with. So the model is not the reality. The other third aspect, very important, that starts our work in classifying different model types. The first classification we have already seen is that between distributed and aggregated parameters models, meaning if you're going to describe spatial heterogeneity of your systems or not. If you're going to describe spatial heterogeneity, you are going to employ a distributed parameter model. If you are not interested in the spatial heterogeneity and you're happy with simply a point, zero-dimensional point model, then you will switch to aggregated parameters. Why this? Because distributed is complex, aggregated is simpler. As we will see, the ecological model will save in order to reduce the complexity of its discussion, of its description, but to reduce the complexity down to a point that the model is still useful. This means that you're not going to reduce it too much, because otherwise the model will tell you nothing about the system, but you will have to reduce it the most as possible in order to make your mathematical model treatable. The idea is that you can always build a more complex model up to a point that you and your computer is not able to manage the model itself. Saying differently, a model, for example, a mathematical model, let's say, that describe the evolution of an environmental system along, for example, 1 month. If you run your model in order to obtain a description that lasts 1 month of your ecological system, but your model is such complex, so complex, that in order to get a run, a complete run, you need to leave your model, in order to leave your model running for 1 entire year, then your model is useless, because you have to wait 1 year in order, 1 year of calculation of your CPU in order to get the description of 1 month. So you understand that your model very quickly becomes untreatable and useless. Okay, somebody says on the chat that on Tuesday morning you have lectures, so we may decide according to change the schedule, or we may switch the lecture in the afternoon. And I would like to discuss among you this, and I would like that the delegate presents the request of the class to me. So unless I do not get any clear demand, my scheduling will be the one I have presented, meaning that on Tuesday morning I have a lecture. If you're not available, or the class agrees, I am open to switch this lecture in the afternoon on Thursday or even on Friday morning, as you prefer. But please discuss this among you and ask the delegate to discuss it or to present your request to me. Okay? Let's see from some example. Okay, we will discuss about model types. You've seen distributed and aggregated. There is another important distinction, that is that between deterministic and stochastic models. This is really an epistemological issue, in the sense that has to do with the way we describe reality, nature. You may remember from your studies in the high school that the deterministic approaches, the so-called Cartesian approach, assumes that there is the possibility of describing in a clear way the consequences, or in a unique way the consequences of some configurations of the system, while the stochastic approach instead takes into play also some aspects that are not in principle foreseeable, so that I have to include in my description some kind of randomness or stochasticity. Classical sciences classical physics is a deterministic science. This means that we may always distinguish the effects of a change made in the configuration of the starting condition of the system, because a change made in the starting condition of the system always produces a changement of the output of your model. This means that in a deterministic term, I can deterministically link the state of a system with its evolution in time. We know modern science understood since the 19th century by the introduction of statistical mechanics that some kind of randomness was always needed in order to have a complete description of a real system. This kind of randomness or stochasticity has to do with our inability of knowing with an arbitrary precision the state of a system. As we will see, this has to do with Heisenberg's indetermination principle. So the real revolution started in the end of 19th century, beginning of 20th century, with the introduction of quantum mechanics in physics. It is a radically different way of approaching our study or analysis or understanding of a reality. So we may immediately classify different models in terms of deterministic and stochastic models if we have or we have not some kind of randomness or random behavior. So that we need to include somewhere in our description statistical analysis. Some example of models that may fall into different classification we have seen here are those, for example, listed in the yellow box. For example, the tailoring. So the models employed for building dresses is a first very simple example of physical model. So when you go to a tailor, the tailor takes some measures about your body size, length of arms, toes, width, diameters, and so on. And by these measures, the tailor employs his tailoring modeling skills in order to build up a dress that fits onto your body. This is an example of how a model may be employed to build or construct physical objects. Wind tunnels is another example of modeling approaches in which, for example, you study the suitability of the shape of a car, for example, in order to optimize this shape in terms of attritus or in terms of resistance against air flows. So you employ wind tunnels that are physical models in which you study a physical phenomenon, how air passes around my cars in order to optimize the object we are going to build, so the cars, the shape of the car. Weather forecasts are another example of very complex mathematical models that describe complex ecosystems, very large complex ecosystems in terms of weather conditions. You know that weather means clouds, not clouds, rain, not rain, cold, hot, and so on. The idea of weather forecasting models is that of providing a forecast or providing a description how the weather of the systems I'm focusing on will be in the future. Weather forecasts are models for which, for example, we have temporal scales of at least days or hours. You will never employ a temporal scale of seconds into a weather forecast because you will never be able to have the CPU availability. So computing availability necessary to solve differential equations. In weather forecast model, the spatial scale will be that of at least a landscape. So this means hundreds of meters, kilometers, sometimes tens or hundreds of kilometers, or even thousands of kilometers, according to the type of weather forecast you need. Again, weather forecast models are models that are some way between deterministic and stochastic models. Weather forecast models are typically distributed parameter models because they change their performance according to the different spatial or geographical location. Other example of model flight simulators. I don't know how many of you have ever played with flight simulators games. Flight simulator games is not more than a mathematical model describing the process of an airplane that flies into the air. So, into the flight simulator modeling, you have a very complex system in which you have a description of the cockpit of an airplane and the possibility of changing the behavior of this airplane in order to perform some particular tasks, like, for example, landing or taking off, and so on. There are other examples of physical model, the physical lagoons, for example, sometimes, in order to understand which are the effects on complex, for example, aquatic ecosystems, structures of different management tasks or different management strategies, we may employ physical models, for example, with a different scale. Instead of having a 1-to-1, so 1 meter in reality, 1 meter in your model, you may have 1-to-10 scale. 1 meter, 10 meter in the reality corresponds to 1 meter in your model, or analogously 10 centimeters in the reality corresponds to 1 centimeter in the model. What you do, you may build a replication of a production of a physical structure or a physical reproduction of an ecosystem and try to study how this system responds to different surrounding conditions. We have such an example here in Padua because we have a physical model of the Lagoon of Venice that have been employed in order to study the effects on the Lagoon of Venice ecosystem of the construction of closures to the lagoon, sea lagoon inlet. So we are trying here in Venice, for some reasons linked to sea level rise, to decide to close or open the Lagoon of Venice by closing or opening the entrances or connections of the lagoon to the sea in order to evaluate the effect of what we have built on the Lagoon of Venice some years ago, that are Mcesy, that are closures that allows us to close the Lagoon of Venice in order to protect the city of Venice from the effect of high tides. We have a growing problem with high tides here in Venice. High tides that are entering, that are affecting the quality of the cities, because the city goes under the level, sea level. So we may employ a physical model in order to study the effect of closing and opening the lagoon. This is what has been done here in Padua. We may discuss about that later. Okay, the general procedure for building a mathematical model, or if you want a mathematical description of a real system, is that the one that I have tried to sketch this graph. We start by formulating some hypotheses. For example, to stay in the realm of environmental engineers, we formulate the hypothesis that increased nutrient load into an environmental systems may end up with eutrophication, so dystrophic algal growth or dystrophic algal blooms. So we formulate this hypothesis. We want to test this hypothesis. Then we go to a second step. So we construct the model. Then we do validity tests. In order to construct the model, we will have a procedure for constructing an ecological model. As I already anticipated, this will be a subject of this week mainly. So we will discuss, go step by step with the procedure of building or constructing the ecological model. Then we check by doing validity tests about the model performance. Can you see my pointer here? Yes, I think. Huh? So we start constructing a model. So we do some, we start by formulating hypotheses. Okay, on the hypothesis, we build up and construct the model. Then we switch to the validity tests. The model passes the validity test. Yes, we can go on. The model does not pass the validity test, then we go back and change the model. So you see this is a kind of iterative procedure. Once the model passes the validity test, the model is said to be validated, and then we are ready to apply the model to different ecosystems. Different from what? Different from the systems, but we are starting by formulating hypotheses on particular example. We need to describe quality status of a lake. So we formulate the hypothesis that nutrient loads that are discharged into the lake may change the biology of the lake so that we have algal blooms. Then we try to test the performance of our models, like for example, by once we have formulated mathematical equations linking, for example, algal concentration to nutrient loads, we shall verify that if we increase the nutrient load, we expect an increase of algal concentration, algae concentration. So if our model responds like we expected, we may say that the model is validated. So we are ready to apply to real ecosystems. In particular, to apply to different systems, we will apply the model to a different lake in order to verify if the model works. Once you apply to different systems, you may recognize that the model needs to undergo some improvements. For example, through the redefinition of the underlying assumption. So we go back to the formulation, initial formulation of the hypothesis. So from the application to real systems, we are ready to start to we have the opportunity, to realize that the model need to be improved. So we go back to the task of model constructions, and we do again valid test and so on. So you see, this is a kind of cyclic procedure. Once we have an approved, validated, satisfying model of the system, then we have built an important tool, what we may say a complete model, that may allow us to go further onto theoretical formulation. So this is to explain you the fact that even if real systems are very complex, too complex, even if our description is limited, even if we may only focus on certain specific aspects of the system, then the result of having a complete working model is important in order to proceed into further theoretical understanding or theoretical formulation. So in this context, we see the mathematical model as the scientific tool that allows the mathematical modeler or the scientist to improve or to deepen his understanding of the system by providing a tool that simulates the behavior of the systems that he is studying. Somebody is asking me to increase my volume. Let's say if I can do that from the control panel. I believe I'm already at maximum level. No, maybe this is a little bit higher, slightly higher. Okay. Let's finish this lecture by giving an overview of different model types. We have already seen that the first classification may be that distinction may be that between physical and mathematical model. Physical models are like the tailoring of a true scale model that a tailor may employ, or physical models may be distorted scale models. Remember, for example, the model of the Lagoon of Venice, but I talked before, in which we have built a physical made of concrete and iron description of the Lagoon of Venice with a distorted scales 1 to 10. Sorry, that was 1 to 50. This means 50 centimeters corresponding to 1 centimeter. And by employing this kind of physical model, we may gain some knowledge, in particular on the management issues related to the management of physical systems. For the mathematical models, instead, we have a much more elaborated classification system. We start from stochastical model versus deterministic model. So models in which we have some aspects that are described in terms of statistical evaluations, or in which some processes are described by introducing some kind of stochastic or random behavior. This is opposite to describe your system by employing a deterministic mathematical model. Deterministic mathematical models are models for which we have well-defined differential equations that may be solved in some way, mathematically or analytically or numerically solved, but in which we have a clear connection between input and output. So nothing is left to statistic or to randomness. Instead, we have equations. Like, for example, all the classical physical models are typically deterministic models. Newton's laws are typically deterministic models, which, for example, we may link the force to the acceleration of a body, the force to which a body is subjected will be acceleration that the body manifests. And the equation is very deterministic in the sense that the coefficients that links these two quantities, forces and acceleration, is the mass. So we may write that force is equal to mass time acceleration, first Newton law, because we are employing a deterministic model in which we know that deterministically a changement on the force causes a changement in the acceleration, and this changement is proportional to the mass of the body. Another important way of classifying models is that between steady state and dynamic model. Steady state models are models for which there is at least one quantity or one descriptor, but does not changes in time. So you understand that a steady state model is not too cool. Steady state meaning that you may add some kind of characteristic. You may, for example, say that a model is steady state toward, for example, the mass density of an object. In this case, you may mathematically write that the derivation in times of a state variable is always zero. The model is steady state. On the contrary, dynamical models that are more complex models are models in which there is no steady state condition, in which everything is changing in time. You understand that the distinction between steady state and dynamic, again, are the two extremes of a possible choice of a characteristic. So we may decide to be very steady state, totally steady state, or we may decide to be totally dynamic. Of course, to be totally dynamic requires a more complex approach, a very highly complex model, while steady state brings within some kind of simplifications. And then from a mathematical point of view, there is of course the distinction we have already seen between distributed and aggregated parameters. And there is also another important characteristics of some mathematical models that is that of changing the structure. We say that these models are structural dynamic models. For example, what this meant in the realm of ecology, it means that the structure of the ecosystem may change, the structure of the model may change in order to reflect changement on the structure of the ecosystem. Example, a new species appears into your ecosystem, then you have to change the structure of your model by adding, for example, a new state variable describing the presence of a new species. Okay. Physical models, again, we are doing some enumerations. Typically, physical models are smaller or larger physical copy of an object. As I already described you, the description of the lagoon of Venice, you use concrete and iron to construct, or plastic or whatever you want, to construct an object, a physical object, that is a copy of the system that you want to describe. That physical model, we can do that, for example, for a ship, in order to describe the effect of a ship floating on water, of a ship navigating into currents, or a ship that is subject to waves. Or we may, for example, employ a physical model to describe an atom. Of course, in the case of a ship, you will employ a reduced scale in order that if your ship is large, then you will reduce the scale in order to construct an object that maybe you can put onto your desk and play with your hands, and you do not need a crane to move your ship. Again, for example, for the atom, models of the atom, instead you use an expanded scale model in which you may physically build a structure that describes the fact that electrons are rounding and running around the nucleus of the atom. In biology or in ecology, there are several ways of building these kind of physical models. Probably the most diffuse is that of using batch reactors. Batch reactors are a situation in which are boxes, if you want, in which conditions are maintained constant. Which conditions? Temperature, humidity, sunlight, presence of pollutants, or quantity of oxygen, and so on. Let's say the environmental conditions are maintained constant, and then you put a population of living objects into the batch reactor in order to see how this living object responds to changing condition to your reactor. On a different scale, there are microcosms that are ways of trying to build ecosystems in a reduced scale in order to see or to study the effect of changing the condition onto the species, the living species that are living into the system. One of these examples, if you go, you can Google search by the Biosphere 2 project. For example, in the desert of Nevada, in the United States, they have built kind of a sucoup, common sucoup in English, kind of covering, glass covering, in which, so very large dimensions, in which they are trying to study the effect of a changing condition onto some species. These kind of studies are, for example, very relevant for the spatial exploration, space exploration program, because it would be of very importance being able to, for example, make agriculture in the space, or make agriculture on Mars if you want to grow something on Mars, in order to understand which are the relevant aspects that will change the performance of the growing system. You may employ a biosphere microcosms model. Okay, topographical models. Topographic models has to do with GIS, Geographical Information System. Topographic models refers to geographical maps that are different representation of a certain portion of the territory, different for different purposes. These models are interesting for the ecological modeler because they are paradigmatic in the sense that the model shall contain all the elements of interest for the intended purposes, but only those. So you are not including all the possible elements onto your model, but you include only the elements that are relevant for the purpose of the model. For example, a geographic map, you will never include vehicles, but you will only include structures, infrastructures like streets, crossroads, buildings, and so on, because vehicles, the distribution of vehicles will change very quickly, making so the roadmap useless. So the vehicles onto a roadmap is an information that is useless. It is just increasing the complexity of a model, increasing the computational demand without giving any advantage. So this is why we say that in order for the model to be useful, you will have just to include those elements of interest. Mathematical models, as I anticipated, are important because they allow to go from the analysis to the synthesis. For example, you may see that an equation may describe the process of grazing. What is grazing? Grazing is an animal that is feeding on grass. Grazing is the typical process that herbivores do in order to feed themselves. So we may find out an equation that links out the process of grazing to the effect of this process onto the increase of the mass of the body of the animal. Point is that even if we can describe very roughly this kind of linkages by finding a very simplified equation, and we will see some example of this kind of equation, the fact that we have this description, this allows us to deepen our understanding of the process. I understand that this sounds to you a little bit weird, but by going into some examples later in the class, you will see that this makes some sense, or you will better understand what we mean by these sentences. Another important class of models, particularly important for the engineers, are the so-called management models. An example of management models, process management, is that of baggage claim systems in airports. The baggage claim system is quite complex because in a larger airport, like for example that of Denver, in which you have tens of flights arriving every moment, every minute, and you have a lot of baggage clusters to be distributed to a baggage distribution system, and typically you do that by employing a management model that is open to but receives the input of these baggages cluster and then decide where to deliver to the baggage claim station. So another important type of management model, or better, another important reasons for building a management model is that of making predictions, so changing the condition, the surrounding condition. If you have a good management model, if you change the surrounding condition, you can have an idea, or you can predict what are the behavior of a system later. As a prediction example, I put economic models. I do this because this is a blague, on dirait en français. In English, this is a joke. Of course, economic models are not precise models, are very, very, very complex. And let's say very untrustable from the results, from the prediction we make. And this arises from the fact when to economic models, there is a crazy variable, uncontrolled, that is human beings. Human beings, by definition, are not very predictable, and this makes very difficult to make predictions with models in which human beings or living things that are by definition unpredictable are a significant part of a system I want to describe. Then typically, if you deal with the problem of environmental pollution, management models are very precious. As the example I already give you, if you're able to describe the process of algal growth into a lake system, into a lake ecosystem, as a consequence of nutrient loads, so we are describing environmental pollution problem, and you have a tool that allows you to see what happens, what if I reduce the nutrient loads, or to what extent I shall reduce nutrient loads in order to have appreciable results in terms of water quality. All these models arises from research models. This is why it is so important to have the ability of building a mathematical model that allows us to build a mathematical model that allows us to pass from the analysis, observation of the system to the synthesis, prediction of the behavior of the system. There is a very general framework, that is the DPS-IR framework, that is a classification of environmental indicators, but is very useful in order to deal with environmental pollution or environmental impact problems. The DPS-IR framework classifies the different quality indicators into drivers, pressures, state, impact, and response. In order to make clear what is meant by this term, I give you a first example. For example, let's consider agriculture. The driver for agriculture is I need to produce food. Then in doing this, I will employ manure or fertilizer, or I will plant the earth, so that I will generate pressures. The pressure is loads of nutrients under the forms of manure and fertilizer. This pressure will generate change in the state of the system. Why this? Because, for example, by soil runoff, you will have that a significant part of the nutrients are discharged into the receiving ditches on the sides of my field. This will cause a change in the state of the system, in which we will have an increase in nutrient concentration into of the water of the ditches receiving the runoff water of my field. And as an impact, you will have algal blooms. algal blooms into the ditch or into the receiving water body. Algal blooms causing the very well-known problem of eutrophication, so destroying the quality of the system, of the ecosystem. Once we realize that we have this kind of connection, so need of doing something, need for humans of doing something for their survival. Generation of pressures. Pressure cause state changes cause an impact, eutrophication. Then I may figure out to have some kind of responses in order to limit these impacts. The responses may act on the driver, or I reduce my need of doing agriculture, or may act on the pressures. For example, I reduce the quantity of fertilizer by changing the way I'm doing agriculture, and so on. I present this model to you because this first classification of indicators, environmental indicators, is the one that has been adopted by all international organisms dealing with environmental impact assessment. Driver pressure, state, impact response. What are models as tools for scientific inquiry? For example, Newton's laws describe the motion of objects subject to gravitational forces. Newton's laws are simplification, meaning that they do not consider, for example, friction. You can always include the effect of friction, but then you have to improve your model, making it more complex. You remember the circular schema we have said, from hypothesis to synthesis. Our observation, the observation of the systems may lead you to improve or to change your models. As I anticipated, the point is that when you deal with complex systems, and believe me, and I will try to demonstrate you that environmental systems are complex systems, we really need the mathematical model as a synthesis tool. So we need a model, but a mathematical tool that allows us to predict the effect of changing the surrounding condition to complex systems. So we have, at this point, two different approaches. The approach of the holistic and reductionistic approach. The holistic approach, that is that typical of biology, ecology, and also ecological modeling as a consequence, is that of describing the entire system by reducing the detail of the individual processes. As we will see, we will not try to include all the detail on all the processes into the ecological model, because the model simply becomes too complex and not manageable even from a computational point of view. So what are the benefits of using models? Allows us to analyze complex systems, to study some very general properties of the system, reveals the limit of our understanding, for example, pushing us into improving further our description, may be used for testing of scientific hypotheses. For the verification of a scientific hypothesis by the use of models, we have four general hypotheses, four cases. The model itself is an hypothesis, of course. So the four cases are we have a correct model, based on correct assumption, or we have a correct model, but we have made a mistake into the assumption. Or we have more likely, this is essentially what happens into the life of the ecological model. We have a wrong model that is based on correct assumptions. This means that our understanding of a system is incomplete. The nightmare for the ecological model is having a wrong model based on wrong assumption. This way, you are really lost into the clouds, lost into the fox. Okay, I think we shall stop here today. Go to a website. I think you will, all the documents, all the material of the courses will be found. Lecture handouts will be found on the website. You have my email, and if you have any doubts, please contact me by email. Okay, I shall close my lecture
Yes,
here. If you have any questions, I wait for you here. If you want to discuss among you, please do that. This is the time. Otherwise, we will see class tomorrow again at 10 beyond the time.